Welcome back, cybersecurity enthusiasts, to episode 16 of our comprehensive cybersecurity course. I'm thrilled to have you join us once again as we continue our deep dive into the fascinating world of digital defense. In our previous episodes, especially within this network security module, we've laid a solid foundation. We've explored network fundamentals, understood how firewalls act as our first line of defense, and learned about various network protocols and their inherent vulnerabilities. We've talked about securing perimeters, encrypting data in transit, and even segmenting our networks to contain potential breaches. But what happens when an attacker manages to bypass these initial defenses? What if a sophisticated threat slips through the cracks? How do we detect these intrusions, and even better, how do we prevent them in real time? That's precisely what we're going to unravel today. Today, in episode 16, titled IDS, IPS and CM, Detecting Cyber Attacks, we're moving beyond mere prevention and into the critical realm of active detection and sophisticated threat management. Think of our current setup like a house with sturdy locks and alarm systems. That's our firewall. But what if someone manages to pick the lock or sneak in through an unmonitored window? We need systems that can either detect their presence immediately or, even better, stop them in their tracks before they cause damage. That's where intrusion detection systems, IDS, intrusion prevention systems, IPS, and security information and event management, CIEM, solutions come into play. We'll explore each of these powerful tools, understand how they work individually and collectively, and even touch upon some industry-leading platforms like Splunk and the ELK stack. By the end of this episode, you'll have a clear understanding of how organizations leverage these technologies to maintain vigilance, analyze security events, and proactively respond to the ever-evolving threat landscape. So, grab your virtual notebooks, because we have a lot of crucial ground to cover. Let's get started. To truly appreciate the value of IDS, IPS, and CIEM, we first need to understand the limitations of our existing security measures, particularly firewalls. In earlier episodes, we celebrated firewalls as the gatekeepers of our network, diligently enforcing rules to permit or deny traffic based on IP addresses, ports, and protocols. And they are, without a doubt, absolutely essential. They act like the security guard at the main entrance of a building, checking IDs and preventing unauthorized people from walking straight in. However, firewalls operate primarily on predefined rules. They're excellent at blocking known bad traffic or traffic that violates established policies. But what if the threat isn't known bad? What if it's an advanced persistent threat, or a zero-day exploit that no firewall rule has been written for yet? What if an authorized user's credentials are stolen, and an attacker logs in legitimately but then starts behaving maliciously? A firewall might see that traffic as legitimate because it adheres to the allowed rules. This is where the analogy of the security guard breaks down. A simple security guard at the entrance might not notice if an authorized employee suddenly starts trying to access restricted areas they shouldn't be in, or if they're attempting to steal sensitive documents. The firewall does its job at the gate, but it doesn't monitor behavior inside the network. It doesn't analyze the context of the traffic. It's like having a locked front door but no internal surveillance system. Attackers are constantly evolving, employing sophisticated techniques to bypass traditional defenses. They might use encrypted tunnels, disguise malicious traffic as legitimate application data, or exploit misconfigurations. These subtle, behavioral deviations or novel attack patterns are precisely what firewalls are not designed to detect or prevent. This introduces a significant gap in our security posture, a gap that demands a more vigilant, analytical, and proactive approach to monitoring and protecting our networks. This critical need for active internal surveillance and response leads us directly to the concept of intrusion detection and prevention. Before we delve into the systems themselves, let's clarify what we mean by intrusion and anomalies in the context of network security. An intrusion isn't just someone breaking through your firewall. It encompasses any unauthorized access, misuse, or tampering with a computer system or network. This could range from an external attacker trying to compromise a server to an insider attempting to steal data or disrupt services. It's any activity that deviates from your organization's security policy or standard operating procedures. Think of it as a breach of your digital boundaries or rules of conduct. Now, how do we identify an intrusion? This is where anomalies come in. An anomaly is simply something that deviates from what is considered normal or expected behavior. Imagine your network is a bustling city. You have regular traffic patterns, people going to work, shopping, communicating. This is normal. An anomaly might be a sudden surge of traffic to a rarely visited part of the city at an unusual hour, or a single person trying to open every single door they encounter. In a network, anomalies could manifest in many ways: an unusual number of failed login attempts from a specific IP address, an abnormally large amount of data being transferred from an internal server to an external, unrecognized destination, a server suddenly communicating with a known malicious command and control server, or even a user account performing actions it has never performed before, like accessing sensitive files at 3 a.m. These anomalies are crucial indicators. They are the digital footprints or unusual sounds that signal something is amiss. They suggest that an activity might be malicious, even if it hasn't been explicitly blacklisted by a firewall rule. Identifying these deviations from the norm requires continuous monitoring, sophisticated analysis, and a deep understanding of what normal looks like in your specific network environment. This understanding forms the bedrock upon which intrusion detection and prevention systems are built, allowing them to flag or block suspicious activities that might otherwise go unnoticed. With the concept of intrusions and anomalies firmly in mind, let's introduce our first major player, the Intrusion Detection System, or IDS. Think of an IDS as the silent, ever-vigilant security camera system of your network. Its primary function is to monitor network or system activity for malicious activity or policy violations and then, critically, to report its findings. It's like that CCTV camera that continuously records everything happening in your building. If someone suspicious enters or attempts something illicit, the camera captures it, and the system might even trigger an alarm, but it doesn't physically stop the person. An IDS doesn't interfere with the network traffic flow. It operates in a passive mode, meaning it observes a copy of the traffic. When it detects something it deems suspicious, it generates an alert. This alert can be sent to an administrator via email, an SMS, or appear on a security dashboard. The key takeaway here is detection and alerting, not prevention. The IDS is your early warning system, giving you crucial time to investigate and respond manually. Its value lies in its ability to identify threats that might have bypassed other initial defenses, providing visibility into potential compromises within your network. There are generally two main categories of IDS based on where they are deployed. First, we have network-based IDS, or NIDS. An NIDS monitors network traffic passing through a specific segment of the network. It's often deployed at key points, such as the perimeter between your internal network and the Internet, or between different network segments. It analyzes packets in real time for patterns that indicate an attack. Second, we have host-based IDS, or HIDS. A HIDS runs on individual servers or workstations. It monitors system calls, file system changes, log files, and other activities specific to that host. For example, a HIDS might detect if a critical system file has been modified or if an unauthorized program is attempting to access sensitive data on that particular machine. Both NIDS and HIDS serve the same detection purpose but operate at different layers of your infrastructure, providing complementary insights into potential intrusions. Not all IDS operate in the same way to detect threats. There are primarily two core detection methodologies: signature-based detection and anomaly-based detection. Let's start with signature-based IDS, also known as knowledge-based or misuse detection. This is the more traditional approach, similar to how antivirus software works. A signature-based IDS maintains a vast database of known attack patterns or signatures. These signatures are specific byte sequences, traffic patterns, or malicious code snippets associated with known viruses, worms, malware, or attack techniques. When network traffic or system activity matches one of these predefined signatures, the IDS flags it as an intrusion. For example, if a specific pattern of commands known to be used by a particular type of SQL injection attack is observed, the signature-based IDS will trigger an alert. Pros: highly accurate for known threats, low false positives for well-defined signatures. Cons: ineffective against new, unknown, or zero-day attacks for which no signature exists yet. It's always playing catch-up, requiring constant updates to its signature database. It's like having a wanted poster for every known criminal. You're great at catching them, but what about the new ones? Next, we have anomaly-based IDS, also known as behavior-based or heuristic detection. This approach takes a different philosophical stance. Instead of looking for what's bad, it first learns what's normal. An anomaly-based IDS builds a baseline profile of normal network traffic and system behavior over a period of time. This baseline includes metrics like bandwidth usage, protocol usage, common ports, login patterns, file access frequencies, and more. Once this baseline is established, the IDS continuously monitors activity, and any significant deviation from this learned normal behavior is flagged as an anomaly and potentially an intrusion. For instance, if a user account that usually logs in from a specific office location suddenly attempts to log in from a foreign country at 3 a.m., or a server that typically only communicates internally suddenly tries to upload large amounts of data to an external cloud storage service, an anomaly-based IDS would flag this. Pros: can detect novel, zero-day attacks, or variations of known attacks for which no signatures exist. Excellent for detecting insider threats or compromised accounts. Cons: can have a higher rate of false positives initially, as it learns and refines its normal baseline. Requires a learning period and careful tuning to distinguish legitimate unusual activity from malicious activity. Many modern IDS solutions combine both signature and anomaly-based detection to offer a more robust and comprehensive defense, leveraging the strengths of both approaches. This hybrid strategy allows them to effectively combat both known and unknown threats. While an IDS is excellent at detecting and alerting, it leaves the actual response to an administrator. This is where the intrusion prevention system, or IPS, steps in. If an IDS is like a security camera that records and alarms, an IPS is like a vigilant security guard who, upon detecting a threat, can physically intervene and stop it in real time. The crucial distinction is prevention. An IPS doesn't just observe, it acts. An IPS is deployed in line with the network traffic. This means all network traffic must pass through the IPS before reaching its destination. When the IPS detects malicious activity, using similar signature-based or anomaly-based detection techniques as an IDS, it can take immediate actions to stop the attack. These actions might include: 1. Blocking the malicious traffic, dropping the offending packets. 2. Resetting the connection, terminating the session between the attacker and the target. 3. Blocking the source IP address, adding a rule to a firewall to permanently block traffic from the attacker's IP. 4. Quarantining, isolating the compromised system or user account. Because an IPS operates inline, it introduces a potential point of failure. If the IPS goes down or has performance issues, it can disrupt legitimate network traffic. Therefore, IPS devices are typically built for high availability and performance. They are designed to process traffic at wire speed to minimize latency. Similar to IDS, IPS also comes in network-based, NIPS, and host-based, HIPS, variants. Network-based IPS, NIPS protects entire network segments by monitoring and blocking network traffic patterns. Host-based IPS, HIPS runs on individual hosts and protects them by monitoring system calls, file system changes, and application behavior, preventing malicious processes from executing or making unauthorized changes. The decision to deploy an IDS or IPS, or both, often depends on the organization's risk tolerance and the criticality of the protected assets. An IPS offers immediate protection, but the risk of false positives blocking legitimate traffic is higher. Many organizations deploy IDS for broader visibility and IPS at critical junctures for immediate, automated defense against high-confidence threats. The combination provides both detection for investigation and prevention for immediate threat mitigation. Understanding what IDS and IPS do is one thing, but knowing where to place them in your network is crucial for their effectiveness. Strategic deployment ensures maximum visibility and protection. Let's look at common placement strategies. For network-based IDS, NIDS, and IPS, NIPS, the key is to position them at points where they can monitor the most critical or highest-risk traffic. 1. At the network perimeter, after the firewall. This is a very common placement. Traffic that has successfully passed through the firewall can then be scrutinized by the NIDS/NIPS. The NIPS can block threats that the firewall missed, while the NIDS provides an alert. This is like having an internal security checkpoint after the main gate. 2. Between network segments, e.g., DMZ to internal LAN. Placing NIDS/NIPS between your demilitarized zone, DMZ, where public-facing servers reside, and your internal network is vital. This acts as a protective barrier, preventing potential compromises of DMZ servers from spreading deeper into your sensitive internal network. Similarly, placing them between different internal VLANs or departments can help detect and prevent lateral movement of attackers within your network. 3. On critical server subnets, deploying a NIDS/NIPS specifically to monitor traffic to and from highly sensitive servers, like database servers, domain controllers, or financial application servers, ensures that these crown jewels are under constant, dedicated surveillance. 4. Internet-facing network, before the firewall. For NIDS. Sometimes, an NIDS can be placed even before the firewall, typically in a tap mode, to observe all incoming internet traffic, including attempts that the firewall would normally block. This provides valuable threat intelligence about who is targeting your network, even if they aren't getting past the initial defenses. For host-based IDS, HIDS, and IPS, HIPS, deployment is simpler as they reside directly on the endpoints themselves. 1. Critical servers, HIDS/HIPS should be installed on all mission-critical servers, web servers, database servers, application servers, to monitor their specific activities, file integrity, and system calls. This provides an additional layer of defense that complements network-level protection. 2. User workstations. Deploying HIDS/HIPS on user workstations is important to detect malware, unauthorized software installations, or suspicious user behavior that could lead to data exfiltration or further compromise. The optimal strategy often involves a multi-layered approach, using a combination of NIDS/NIPS at strategic network choke points and HIDS/HIPS on individual critical hosts. This provides defense in depth, ensuring that even if one layer is bypassed, another is there to detect or prevent the intrusion. Proper placement is not a one-size-fits-all solution. It requires a thorough understanding of your network architecture, asset criticality, and potential attack vectors. We've established that IDS and IPS are incredibly powerful tools for detecting and preventing intrusions. They are fundamental components of a robust network security strategy. However, as organizations grow, as their networks become more complex, and as the sheer volume of security events skyrockets, a new challenge emerges: the problem of scale, correlation, and context. Imagine you have dozens, hundreds, or even thousands of IDS/IPS sensors deployed across your enterprise. Each of these devices is constantly generating alerts. A single NIDS might flag hundreds of suspicious packets per hour. A HIDS on a busy server could log thousands of system events. Multiplied across an entire organization, this quickly leads to a deluge of security alerts and log data. Here's where the limitations become apparent. 1. Alert overload. Alert fatigue. Security analysts can quickly become overwhelmed by the sheer volume of alerts. Many of these might be low priority, benign, or even false positives. Sifting through this noise to find the truly critical threats is like finding a needle in a haystack that's constantly growing. This leads to alert fatigue, where legitimate threats might be missed because analysts are desensitized or simply don't have the capacity to investigate every single alert. 2. Disparate data sources. Alerts don't just come from IDS/IPS. They come from firewalls, servers, routers, switches, antivirus software, authentication systems, cloud services, and countless other security and operational tools. Each system generates its own logs and alerts in its own format. There's no centralized view, no single pane of glass to aggregate and normalize all this information. 3. Lack of context and correlation. An isolated alert from an IDS might seem minor. For example, user A failed login 3 times on server X. But what if, at the exact same time, a firewall logs an attempt to connect to a known malicious IP address from user A's workstation, and a HIDS on server X logs an attempt to access a sensitive database by an unknown process? Individually, these alerts might be trivial. But when correlated and viewed in context, they paint a clear picture of a coordinated attack or a successful compromise. Without a centralized system to collect, analyze, and correlate these events, connecting the dots becomes a manual, time-consuming, and often impossible task. This complex landscape, characterized by data silos, alert storms, and a desperate need for contextual intelligence, highlights the critical necessity for a higher-level security management solution. We need a system that acts as the brain, collecting all these disparate pieces of information, making sense of them, and providing actionable intelligence. This brings us to our next major topic, Security Information and Event Management, or SIEM. To address the challenges of scale, disparate data, and alert fatigue, organizations turn to SIEM, Security Information and Event Management. Think of SIEM as the central brain or the command center of your entire cybersecurity operation. If IDS are the cameras and IPS are the guards, then SIEM is the highly skilled detective in the control room, monitoring all feeds, connecting all the pieces of evidence, and raising immediate, contextualized alerts when a serious threat is identified. SIEM solutions integrate 2 core functionalities. 1. Security Information Management, SIM. This focuses on the long-term storage and analysis of security event data. It's about collecting, normalizing, and storing log data from virtually every device and application in your network for forensic analysis, compliance reporting, and historical trend analysis. 2. Security Event Management, SEM. This focuses on real-time monitoring, correlation of events, notifications, and dashboards for immediate incident response. It's about identifying active threats as they unfold. Together, SIEM provides a holistic view of an organization's security posture. Here are its core functionalities: log collection and aggregation. SIEM systems collect log data from every possible source imaginable: firewalls, IDS/IPS, servers, operating systems, applications, routers, switches, endpoint protection, cloud services, and more. All this data, often in different formats, is pulled into a central repository. Data normalization. Once collected, the SIEM normalizes the diverse log formats into a common, structured format. This is crucial for consistent analysis and correlation across different data sources. Event correlation. This is the heart of SIEM. It applies sophisticated rules and algorithms to analyze multiple events from different sources to identify patterns that indicate a security incident. For example, it can correlate a failed login attempt from an IDS with a firewall block, and a specific user's web activity to identify a brute force attack or a compromised account. Real-time alerting. Based on correlation rules, CIEM generates actionable alerts for security teams, prioritizing them based on severity. These alerts can trigger automated responses or workflows. Reporting and compliance. CIEM systems are invaluable for compliance mandates, like HIPAA, GDPR, PCI DSS. They can generate detailed reports on security events, user activity, and compliance violations, demonstrating that an organization is meeting regulatory requirements. Forensic analysis. In the event of a breach, the aggregated and indexed data in a CIEM is critical for incident response teams to perform forensic investigations, understand the attack timeline, identify the point of entry, and assess the damage. In essence, a CIEM transforms a flood of raw security data into meaningful, actionable intelligence, enabling organizations to detect, analyze, and respond to cyber threats more effectively and efficiently. It brings clarity to chaos, empowering security teams to focus on true threats rather than chasing down individual, isolated alerts. To understand how a CIEM achieves its powerful capabilities, let's break down its core components and visualize the typical workflow. It's a structured process designed to transform raw, chaotic log data into actionable security intelligence. Here's a typical CIEM workflow and its key components. 1. Log sources. Data generation. Every device and application in your network is a log source. This includes firewalls, routers, switches, operating systems, Windows, Linux, applications, web servers, databases, intrusion detection/prevention systems, antivirus software, cloud environments, and more. Each of these sources continuously generates event logs detailing their activities, from successful logins to system errors to blocked network connections. 2. Log collection and aggregation. This is the first step where data enters the CIEM ecosystem. Collectors/agents. The CIEM deploys agents on individual hosts, like servers or workstations, or uses agentless methods, like syslog, SNMP traps, WMI for Windows event logs, or API integrations for cloud services, to pull or receive log data from all the various sources. These collectors ensure that logs are gathered efficiently and often securely. Aggregators. All the collected data is then aggregated into a central point, often compressing and encrypting it for transmission to the core CIEM system. 3. Data normalization and parsing. Once aggregated, the raw log data, which comes in myriad formats, e.g., plain text, XML, JSON, is then processed. Parsers. The CIEM uses parsers to understand the structure of each log type. These parsers extract relevant fields, like source IP, destination IP, username, event type, timestamp, severity, and transform them into a common, standardized format that the CIEM can work with. This normalization is critical for consistent analysis and correlation. 4. Data storage. Database. The normalized event data is then stored in a high-performance database. This database needs to be robust, scalable, and optimized for fast querying and retrieval, as security analysts will frequently access this historical data for investigations and reporting. Often, this involves distributed storage and indexing technologies to handle petabytes of data efficiently. 5. Correlation engine. This is where the magic happens. The correlation engine applies a set of predefined rules, often highly customizable, to analyze the normalized event data in real time. It looks for patterns, sequences, and relationships between seemingly unrelated events that might indicate a security incident. For instance, if it sees 5 failed login attempts from a specific IP address within 1 minute, followed by a successful login from a different IP address for the same user, it might flag this as a potential brute force attack followed by account compromise. It can also use machine learning to identify anomalous behavior. 6. Alerting and dashboards. When the correlation engine identifies an event that matches a rule or an anomaly, it generates an alert. These alerts are then displayed on a centralized dashboard, often with visualizations, charts, and graphs that provide a clear overview of the organization's security posture. Analysts can drill down into specific alerts for more detail. Alerts can also be configured to trigger notifications, email, SMS, or even automated responses, e.g., blocking an IP address via a firewall integration. 7. Reporting and analytics. Beyond real-time alerting, CIEMs provide powerful reporting capabilities for compliance auditing, security posture assessments, and long-term trend analysis. This allows organizations to track security metrics, identify recurring threats, and demonstrate adherence to regulatory standards. This comprehensive workflow ensures that raw data is transformed into meaningful, actionable security intelligence, making the CIEM an indispensable tool for modern cybersecurity defense. When discussing CIEM, two platforms often dominate the conversation: Splunk and the ELK stack. Let's start with Splunk, which is arguably one of the most widely recognized and powerful CIEM solutions available today. Splunk often markets itself as a data-to-everything platform, and while it has broader applications, its strength in security information and event management is undeniable. At its core, Splunk is a powerful engine for searching, monitoring, and analyzing machine-generated big data. It excels at collecting, indexing, and correlating vast quantities of log and event data from virtually any source in real time. For security teams, this means unparalleled visibility into their entire IT infrastructure. Here's why Splunk is so popular in the CIEM space: universal data collection. Splunk can ingest data from almost any source, regardless of format. Whether it's structured data, unstructured data, logs from Windows, Linux, network devices, applications, or cloud services, Splunk can handle it. Powerful Search Processing Language, SPL. This is Splunk's crown jewel for analysts. SPL is a highly flexible and powerful language that allows users to perform complex searches, filter data, create correlations, calculate statistics, and transform raw logs into meaningful insights. For example, a simple SPL query might be index equals web source type equals access underscore combined status equals 404 stats count by client IP, which would count all 404, page not found, errors on web servers, grouped by the client IP address. You can build incredibly sophisticated queries to detect specific attack patterns or behavioral anomalies. Real-time monitoring and alerting. Splunk can continuously monitor incoming data streams and trigger alerts based on defined search criteria or thresholds. This allows security teams to be notified immediately when a critical event or attack pattern is detected. Dashboards and visualizations. Splunk provides rich, customizable dashboards that allow security analysts to visualize key metrics, trending data, and real-time security posture. These visualizations make it easier to identify trends, pinpoint anomalies, and present complex information clearly. App ecosystem. Splunk has a vast ecosystem of apps and add-ons in its Splunk-based marketplace. Many of these are specifically designed for security, providing pre-built dashboards, reports, and correlation rules for common security tools and compliance frameworks. Splunk Enterprise Security, ES, is a premium security app that transforms Splunk into a full-fledged, advanced CIEM, offering capabilities like incident management, risk scoring, and threat intelligence integration. Scalability. Splunk is designed to scale horizontally, allowing organizations to ingest and analyze petabytes of data across distributed environments. While powerful, Splunk can be resource-intensive, and its licensing model is based on data ingestion volume, which can be a significant cost consideration for large enterprises. However, its comprehensive features and robust capabilities make it a top choice for organizations seeking deep security visibility and advanced threat detection. On the other side of the CIEM spectrum, especially popular in the open-source and cloud-native communities, we find the ELK stack. Now officially known as the Elastic Stack, it's a collection of three powerful open-source projects: Elasticsearch, Logstash, and Kibana. These components, when combined, provide a powerful solution for log management, search, and visualization, making it a highly capable and cost-effective alternative for SIEM functionalities. Let's break down each component. 1. Elasticsearch. This is the heart of the ELK stack. Elasticsearch is a highly scalable, distributed, open-source search and analytics engine. It's built on Apache Lucene and is designed to store, search, and analyze large volumes of data very quickly. For SIEM purposes, it acts as the central data store and indexing engine for all your security logs and events. Its ability to perform full-text searches and aggregate data in real time makes it incredibly powerful for security investigations. 2. Logstash. Logstash is a dynamic data pipeline that ingests data from various sources, transforms it, and then sends it to a stash, most commonly Elasticsearch. It's incredibly flexible, capable of collecting data from almost any source, syslog, files, databases, Kafka, etc. Critically, Logstash includes a wide array of filters that allow you to parse, enrich, and normalize your log data before it's stored in Elasticsearch. For example, it can extract specific fields from unstructured logs, geolocate IP addresses, or anonymize sensitive information, making the data much more useful for security analysis. 3. Kibana. Kibana is a powerful, open-source data visualization and exploration tool. It sits on top of Elasticsearch and allows users to interact with their data through customizable dashboards, charts, and graphs. For security analysts, Kibana provides the single pane of glass to visualize security events, track metrics, identify trends, and drill down into specific logs during an incident investigation. You can build dashboards to show top attacking IPs, types of security events, failed login attempts over time, or network traffic anomalies. How they work together. Logstash collects and processes logs from all your security devices and applications. It normalizes this data and then forwards it to Elasticsearch, where it's indexed for rapid searching. Finally, Kibana connects to Elasticsearch to provide a rich, interactive interface for exploring and visualizing all the aggregated security information. The ELK stack offers immense flexibility and scalability, making it a favorite for organizations looking for powerful log management and SIEM capabilities without the proprietary licensing costs of some commercial solutions. While it requires more setup and configuration effort than a turnkey solution, its open-source nature, active community, and powerful capabilities make it an attractive option for many cybersecurity teams. Many organizations also supplement ELK with additional tools like Beats, lightweight data shippers, and XPack, Elastic's commercial security, alerting, and monitoring features, to build a comprehensive security analytics platform. Understanding IDS, IPS, and SIEM is foundational, but the real power comes from effectively analyzing the logs these systems collect. Log analysis is the detective work of cybersecurity. It's about sifting through vast amounts of data to find the subtle clues that indicate a cyber attack. Whether you're using a full-blown SIEM like Splunk or ELK, or even just reviewing raw logs, knowing what to look for is paramount. Let's walk through some practical examples of log analysis for threat detection. Imagine you're a security analyst looking at a stream of aggregated logs. What are some common indicators of compromise, IOCs, you'd be searching for? 1. Failed login attempts. What to look for: a high number of failed login attempts from a single source IP address to multiple accounts, or to a single account from multiple IPs, especially outside business hours. Example log pattern: event_type equals failed_login user equals admin src_IP equals 192.168.1.100 repeatedly, then suddenly event_type equals successful_login user equals admin src_IP equals 203.0.113.5. This could indicate a brute force attack followed by a successful compromise, possibly from a different location via a proxy. 2. Unusual traffic patterns. what to look for: outbound connections to unusual destinations, e.g., known bad IPs, unapproved cloud storage, abnormally large data transfers, or connections on non-standard ports. Example log pattern: a web server, src_IP equals 10.0.0.5, that usually serves web pages on port 80/443 suddenly initiates an outbound connection to a foreign IP address, dst_IP equals 185.x.x.x, on an uncommon port, dst_port equals 5357. This could signal command and control, C2, communication or data exfiltration. 3. Unauthorized access or escalation: what to look for: a standard user account attempting to access highly restricted files or directories, or a user account trying to gain administrative privileges, privilege escalation. Example log pattern: event_type equals file_access user equals do path equals / etc. / shadow_password result equals denied. Followed by event_type equals privilege_escalation user equals do result equals success. This indicates an attempt to access sensitive files, followed by a successful elevation of privileges, which is a major red flag. 4. Malware activity: what to look for: antivirus alerts, execution of unknown processes, suspicious file creations or modifications, or unexpected outbound connections from endpoints. Example log pattern: an antivirus log showing detection equals Trojan, emotet file equals C, /users /public /malware.exe. Or a system log showing a new, unsigned executable running from a temporary directory. 5. Configuration changes: what to look for: unauthorized or unexpected changes to firewall rules, user accounts, system settings, or critical application configurations. Example log pattern: a firewall log showing action equals rule_added source_IP equals any destination_port equals 22. An unapproved change that opens up SSH access could be an attacker creating a backdoor. 6. Geolocation anomalies: what to look for: a single user account logging in from geographically disparate locations within a short time frame, e.g., New York and then Beijing within an hour. This is physically impossible and indicates account compromise. Effective log analysis often involves knowing your network's baseline, having up-to-date threat intelligence, lists of known bad IPs, domains, and malware hashes, and employing a combination of signature-based, looking for known bad strings, and anomaly-based, looking for deviations from normal, detection techniques. The CM is critical here because it aggregates and normalizes these logs, making these complex correlation tasks much more manageable and efficient for security analysts. It's the ultimate tool for turning raw data into meaningful security insights. As we wrap up this dense but crucial episode 16, let's consolidate the key takeaways. Today, we've elevated our understanding of network security beyond basic perimeter defenses to sophisticated, active threat detection and response. We started by recognizing the limitations of firewalls and the necessity for active detection against evolving cyber threats, introducing the concepts of intrusions and anomalies. Then, we delved into intrusion detection systems, IDS, which act as our network's silent observers, monitoring traffic and system activity for malicious patterns or policy violations and generating alerts. We learned about its two primary forms: signature-based IDS, effective for known threats by matching predefined patterns. Anomaly-based IDS, powerful for detecting zero-day attacks and insider threats by identifying deviations from normal behavior. Following that, we explored intrusion prevention systems, IPS, which take detection a step further by actively blocking or dropping malicious traffic in real time, functioning as our network's active enforcer. We discussed the critical difference: IDS detects, IPS prevents. We also covered various deployment strategies for both NIDS/NIPS, network-based, and HIDS/HIPS, host-based, to ensure comprehensive coverage. Next, we acknowledged the inherent challenge of managing an overwhelming volume of alerts from disparate security tools, which led us to the Grand Orchestrator, Security Information and Event Management, SIEM. We learned that SIEM is the central brain, responsible for collecting and aggregating logs from all devices, normalizing this data into a usable format, correlating seemingly unrelated events to identify complex attack patterns, providing real-time alerts and comprehensive reporting for compliance and forensic analysis. We then took a closer look at two leading SIEM solutions, Splunk, a powerful, enterprise-grade platform known for its universal data ingestion, advanced search processing language, SPL, and rich dashboards, ideal for large-scale security analytics. The ELK stack, Elasticsearch, Logstash, Kibana, a popular open-source alternative offering flexible log collection, powerful search capabilities, and intuitive visualizations, especially favored in cloud-native and cost-conscious environments. Finally, we wrapped up with a practical session on log analysis for threat detection, emphasizing how to identify critical indicators of compromise such as failed login attempts, unusual traffic, unauthorized access, and malware activity by effectively querying and understanding the log data aggregated in a SIEM. In essence, these systems, IDS, IPS, and SIEM, are not isolated tools. They form a crucial, layered defense mechanism. IDS provides visibility, IPS offers immediate protection, and SIEM binds everything together, providing the overarching intelligence needed to understand, respond to, and ultimately defeat cyber attacks. Mastering these concepts is fundamental to building a resilient and proactive cybersecurity posture. And that brings us to the end of episode 16. I hope you found this deep dive into IDS, IPS, and SIEM incredibly insightful. Understanding these detection and management systems is absolutely critical for any aspiring cybersecurity professional or anyone looking to bolster their organization's defenses. The ability to not just block but to see and understand what's happening in your network is what truly separates advanced security teams from the rest. We've covered a lot of ground today, moving from perimeter defense to the core of internal vigilance and incident intelligence. I encourage you to revisit these concepts, perhaps even explore the free trials or community editions of tools like Splunk or the ELK stack to get some hands-on experience with log analysis. There's no substitute for practical application. Before you go, if you found this episode valuable, please give it a thumbs up. It really helps the channel and motivates us to create more high-quality content for you. Don't forget to subscribe to the channel if you haven't already, and hit that notification bell so you don't miss any future episodes of our cybersecurity course. And as always, your thoughts and questions are incredibly important to us, so please leave a comment below with any insights or topics you'd like to see covered further. So, what's coming up next in episode 17? Having discussed network detection, we're going to shift our focus to vulnerability management and penetration testing. We'll explore how organizations proactively identify weaknesses in their systems before attackers do, and how ethical hackers simulate real-world attacks to test defenses. It's an exciting episode that will tie together many of the concepts we've learned so far into practical security assessments. You won't want to miss it. Thank you again for being a part of this journey. Stay curious, stay vigilant, and I'll see you in the next episode.